Jnanam Paramam Dheyam. Knowledge is supreme.
In the last lecture, we looked at the design of packed bed reactor, which is operated under external mass transport limitations. And we particularly looked at what is the way to achieve or find the expression for the conversion as a function of the mass transport coefficient. And we found that conversion is essentially given by 1 minus exponential of minus Kc Ac divided by U into length of the reactor. So, Kc is the mass transport coefficient, for the species to diffuse from bulk to the surface of the catalyst pellet, and Ac is essentially the surface area per unit volume, external surface area per unit volume. And U is the superficial velocity. And L being the length of the bed. So, often the question is, how do we improve the conversion of a given reactor? So, we know what is the conversion as a function of the mass transport coefficient, external surface area which may be available in the bed, and the superficial velocity. So, if we have to find out how to improve the conversion for a given reactor and given catalyst and given reaction, whose intrinsic kinetics is fixed, and the reactor is operated under external mass transport limitations. So, one way to do that is actually by tweaking this mass transport coefficient. If we can improve the mass transport coefficient somehow, then we will be able to improve the conversion to a great extent. So, let us see how to do that. So, we first have to find out how the mass transport coefficient depends on the other operating parameters. Now, earlier in a couple of lectures ago, we looked at how mass transport coefficient depends upon the operating conditions when the fluid is actually flowing past a single particle or single catalyst pellet. Now, the fluid is actually flowing past through a packed bed reactor. So, therefore, we need to look at how mass transport coefficient is affected in the whole reactor system, which is actually packed with catalyst, unlike the case where we looked at before, where it was just a single catalyst pellet. In that case, in the case of single catalyst pellet, we actually took advantage of the boundary layer analogy, and we related the mass transport coefficient which is present in Sherwood number to the Reynolds number and Schmidt number using the Froehsling correlation. But that correlation unfortunately cannot be used here, because this system is flow through the packed bed, where there are several particles which are actually packed inside the bed. So, let us look at how to characterize mass transport coefficient, or how to estimate mass transport coefficient in a packed bed reactor design. So, clearly the conversion is a function of the mass transport coefficient, the area per unit volume available for reaction, superficial velocity, and the length of the bed. Now, suppose if I want to improve the conversion, one way I could do is I can actually improve the mass transport coefficient. Now, how do we estimate mass transport coefficient? There are specific correlations which are actually available for flow through beds. For flow through packed beds, the correlation which actually captures the mass transport coefficient is what is called as the famous Thonis-Kramer correlation. And in fact, this correlation is valid for fluidized bed reactors as well. and the correlation is Sherwood number, some modified Sherwood number is equal to some modified Reynolds number into Schmidt number to the power of 1 by 3. So, this modification is essentially to account for the fact that the system that we are considering is a full packed bed which contains several particles. So, this is essentially the Thouless-Kramer correlation, and let us define what these parameters are. So, the Sherwood number, modified Sherwood number, is the Sherwood number of the system multiplied by phi, which is the porosity, divided by 1 minus phi into 1 by what is called as the shape factor. So, phi is the porosity of the bed and this is the shape factor. We will see in a bit, we will see an example where how to actually estimate the shape factor, and the next parameter here is the modified Reynolds number, which is essentially given by Re divided by 1 minus phi into the shape factor. Once again, phi is the porosity of the bed and this quantity is the shape factor, and Schmidt number essentially is the same as what we saw before, which is the kinematic viscosity divided by the corresponding diffusivity at the operating conditions. So, now if we know the parameters of a given system, then we should in principle be able to estimate the modified Sherwood number, modified Reynolds number and modified Schmidt number. So, if I now plug these into the Thouless-Kramer correlation, plug the modified expressions for these different dimensionless quantities, we will see that the Thouless-Kramer essentially boils down to Kc into equivalent particle diameter dP dAB multiplied by phi divided by 1 minus phi into 1 by shape factor, and that should be equal to U dP into rho by mu, which is nothing but the Reynolds number based on the particle diameter to the power of half into mu by rho dAB, which is the Schmidt number to the power of 1 by 3. So, now if we know the parameters as a function of the particle diameters, if we estimate the parameters as part of the taking the particle diameter as the representative diameter, then we should be able to express the correlation in terms of the particle diameter and taking into account the bed properties such as porosity and the shape factor, which takes into account different geometries. So, thus we can actually estimate, this correlation can be used to estimate the mass transport coefficient for the packed bed based on the dimensionless quantities estimated using the equivalent particle diameter and we can account the presence of the bed using the corresponding porosity and the other properties. So, the equivalent particle diameter essentially helps in using this correlation for different geometries. Suppose if I keep all the properties constant, for the whole system, that is the catalyst bed, the flow rate, so on and so forth, temperature, etc. Then as we estimated for the single particle case, even here as well the mass transport coefficient K is actually proportional to U to the power of half, that is the superficial velocity to the power of half. So, therefore, by actually changing the superficial velocity, one can actually achieve a higher mass transport coefficient by increasing the superficial velocity. Of course, one cannot increase it significantly, it depends upon the nature of the setup that is being used. So, there is always there may be an upper limit on how much the superficial velocity can actually be increased. So, suppose I fix the concentration, suppose for a fixed concentration of, let us say, species A which is undergoing reaction. Let us say that the fixed concentration is some Ca, then the overall rate is now going to be proportional to the mass transport coefficient into the concentration of the species, and we know that from the correlation, from the Thonis-Kramer correlation, we know that Kc is actually proportional to the superficial velocity to the power of half, and therefore, the overall reaction rate is essentially going to be proportional to the square root of the superficial velocity. So, by controlling the superficial velocity with which the species is actually feed stream is flowing through the reactor, one should be able to actually modulate the observed reaction rate for the reaction that is happening in a packed bed packed with the catalyst. Now, note that this works only if it is a mass transport limited conditions. This is valid only for external mass transport limited conditions. Now, if we suppose, let us say, we increase the velocity significantly, then it may turn out that the external mass transport limitations are no more there. So, therefore, the dependency of the overall reaction rate on the velocity with which the fluid is actually flowing is valid only when the external mass transport limited regime. And in fact, we looked at, for a single particle case, we looked at the situation where if I look at u by dp power of half and the overall rate, we observed that there is a region where it is external mass transport limited control, after which the overall rate at which the reaction happens is independent of the velocity. So, clearly there is an upper limit to which the velocity, superficial velocity can be increased, where the reaction rate is a function of the superficial velocity. After that point, how much ever the superficial velocity is increased, the overall rate increase is going to be very marginal, because the external mass transport limitation assumptions is no more valid. So, for most mass transport correlations are typically available in terms of a factor called Kolben factor, and the symbol that is used for Kolben factor is JD, which is essentially given by Sherwood number divided by Reynolds number into Schmidt number to the power of 1 by 3. So, instead of Thonis-Kramer, another way to estimate the mass transport coefficient Kc is by estimating the Kolben factor. So, if we know the Kolben factor, then we can actually use this expression here. We can use this expression to find out the Sherwood number, which is essentially given by Kc divided by dAb into the particle diameter, and that is essentially equal to JD into Re into Schmidt number to the power of 1 by 3. Note that for this kind of a correlation where JD is used, the particle diameter is typically given as the available area for the reaction divided by pi. It is not the equivalent particle diameter that is used. The one that usually works is the particle diameter based on the available area for the reaction to happen. Let us say the external surface area where the reaction happens when there is external mass transport limitations. So, this Kolben factor of course is a function of the Reynolds number, and we will let us see how that depends on the Reynolds number, which actually captures the captures the velocity with which the fluid stream is actually flowing through the reactor. So, if I now use a log scale for Reynolds number, let us say 1 and 10 and so on up to let us say 10,000 here. And this is log scale. And if I now plot phi b JD, which is the porosity of the bed, then it actually follows an inverse power law behavior. So, the typical curve or the correlation between the phi b JD and Reynolds number is essentially an invert, and most of the experimental data that has been done for finding the Colburn factor as a function of Reynolds number, they are essentially fall along this inverse power law behavior. And in fact, this can actually be found, the relationship of this line is essentially given by phi b JD is equal to 0.4548 into the Reynolds number to the power of minus 0.4069. So, this is the correlation. Now, there are many different types of correlations which are actually available for the flow through packed beds, for estimating the Colburn factor for flow through packed beds under different conditions. And there is a correlation which essentially summarizes all these different correlations which are available for different conditions and different systems. So, different correlations available for finding the Colburn factor. So, there is a generalized correlation which is applicable for both gases and liquids under a different range of Reynolds number. So, a general correlation which is applicable for both gases and liquids is essentially given by phi times JD, which is again the porosity of the bed, is equal to 0.765 divided by Reynolds number to the power of 0.82 plus 0.365 divided by Reynolds number to the power of 0.385. And this is typically valid for gases when the Reynolds number is greater than 10, and for liquids when the Reynolds number is actually greater than 0.01. And normally when the reactor is operated, the Reynolds number is typically for gas streams is typically more than 10, and for liquids is typically more than 0.01. So, therefore, the general correlation that is here is actually valid for wide range of Reynolds number for both gases and liquids, and therefore, this correlation is actually quite widely used to estimate the mass transport coefficient based on the Reynolds number, Schmidt number, and the Colburn factor JD. So, once we know the Colburn factor, which actually uses the Reynolds number and Schmidt number to relate the Sherwood number to Colburn factor, we can actually find out what is the mass transport coefficient for a given condition. So, let us next look at a very specific example. We will take an example problem where the packed bed reactor is operated under external mass transport limited conditions. So, the specific example we are going to look at essentially is being taken from the textbook in Fogler textbook, page number 785, and we are going to specifically look at the case of decomposition of hydrogen in a packed bed reactor with catalyst being alumina support iridium catalyst. So, that is the catalyst that is used, and we assume that the reaction is conducted under external mass transport limitations. Assume that it is conducted under external mass transport limitations, and let us look at what are all the parameters that are actually available, what are the properties of the system that are actually available. So, the feed is essentially 2% hydrazine in 98% helium mixture, that is the feed, and the catalyst properties are, it is a cylindrical catalyst, and the diameter of the catalyst is 0.25 centimeter dia, and the length of the catalyst is 0.5 centimeter. And it is, and the properties with which the reactor is operated is, the superficial velocity is 15 meters per second, and the temperature at which the reactor is operated is 750 Kelvin, and we assume that the kinematic viscosity of helium at 750 Kelvin is essentially given by 4.5 into 10 power minus 4 meter square per second, and we also assume that the equimolar counter diffusivity of the species is 0.69 into 10 power minus 4 meters per second at 298 Kelvin, and we assume that the porosity of the bed is actually 0.3. So, the question that we need to answer, the question is what will be the conversion? The question is what will be the conversion? What is the conversion at the exit if the length of the bed is equal to 0.5, if the length is essentially 0.05 meters is the length of the reactor. So, we need to find out what is the conversion. So, how do we go about solving this problem? We have all the parameters, and we have said that it is actually external mass transport limitations, external mass transport limitations. So, how do we solve this problem? So, when we looked at the packed bed reactor design, we actually found out what is the relationship between the conversion and the mass transport coefficient. So, let us start looking at that. So, in a packed bed reactor under external mass transport limitations, we found that the conversion essentially is given by 1 minus exponential of minus Kc Ac divided by U into L of the reactor, where L is the length of the reactor. So, we need to find out what is Kc, we need to find out the area per unit volume, and superficial velocity is given. So, once we find these two, we are done. We should be able to estimate what is the conversion of the reactor at the exit of the packed bed reactor, whose length is essentially is equal to L. So, L is given, U is given, we need to find Kc and Ac. So, how do we find Kc? We can use two methods to do that. We describe two different methods by which we can estimate Kc, where first approach for estimating Kc is by using the Thones-Kramer correlation. But we can also use the other method of the Kolben JD factor correlation. We can use the correlation for finding the Thones-Kramer and Kolben JD factor. So, what we will do is we will basically use both these approaches, and we will find out what is the mass transport coefficient under the given conditions when we use Thones-Kramer correlation, and also when we use the Kolben JD factor correlation. and we will compare what is the conversion that we will achieve by using these two different approaches or different correlations for finding the mass transport coefficient. Now, what are the dimensionless quantities we need to estimate? Suppose if it is the Thonis-Kramer correlation approach, then what are the quantities we need? We need the modified Sherwood number which contains the mass transport coefficient. In order to find the modified Sherwood number, we need to find out the modified Reynolds number, we need to find out what is the Schmidt number. But suppose if we use the Kolban JD factor, then we need to find out what is the Sherwood number based on the corresponding definition of dP, the particle diameter, and we need to find out what is the Reynolds number to find the which essentially is used to find the Kolban factor JD, and then we need Sherwood number to calculate the mass transport coefficient based on these four quantities, that is by Reynolds number, JD, Schmidt number and Sherwood number, which essentially contains the mass transport coefficient. So, if we know these three, then we can actually find out what is the mass transport coefficient. And once again in this case as well, once we know the modified Sherwood number from the correlation, we can find out what is the mass transport coefficient. So, let us start by the first approach of using the Thonis-Kramer correlation. So, what is the Thonis-Kramer correlation? The Thonis-Kramer correlation is essentially given by the modified Sherwood number is equal to 1 into modified Reynolds number to the power of half into Schmidt number to the power of 1 by 3. Now, what is the Reynolds number? Reynolds number, modified Reynolds number is essentially given by Reynolds number based on particle diameter divided by 1 minus phi into the shape factor, and that is equal to u into the equivalent particle diameter dP divided by the kinematic viscosity nu, that into 1 by 1 minus phi into the shape factor. Now, note that this is kinematic viscosity and this is the shape factor. So, what is the first step in doing this? We need to estimate what is the equivalent particle diameter, because the particle that we have is actually a cylindrical particle, and this definition is essentially for spherical particles. So, we need to find out what is the equivalent diameter of the particle that is actually being used. Now, how do we find the equivalent particle diameter? We can actually do what is called as the volume averaged. So, the equivalent particle diameter dP can be calculated by using the volume average So, dP essentially is given by the 6 times the volume of the cylinder divided by pi whole to the power of 1 by 3. Essentially, we are finding out what should be the diameter of an equivalent spherical particle which occupies the same volume as that of the cylinder. So, suppose let us say we sketch the cylinder here. The diameter of the cylinder, let us say d is equal to 0.25 centimeters, that is 0.25 centimeters, and the length of the, which is basically the length of the cylindrical catalyst pellet, that is essentially equal to 0.5 centimeters. So, now how do we find this? What is the volume of the cylinder? We do know what the volume of the cylinder is. So, this is essentially given by 6 into pi d square by 4 into the length of the cylindrical particle divided by pi to the power of 1 by 3. So, we can now substitute these numbers. So that will, so pi will cancel out. So it will essentially be 6 by 4 into 0.25 into 10 power minus 2 square into 0.5 into 10 power minus 2, that raised to the power of 1 by 3. So that is essentially equal to 3.61 into 10 power minus 3 meters. So the equivalent particle diameter for the cylindrical catalyst pellet that is actually considered in this problem is given by 3.61 into 10 power minus 3. So what we will see from the next class is we will take forward from the equivalent particle diameter we estimated from here, and we look at the other parameters, estimate the other dimensionless quantities, and we will find out what is the mass transport coefficient using the Thonis-Kramer correlation method and estimate the conversion. Further, we will go ahead and look at the Kolben-JD factor correlation method, and we will estimate the conversion based on that method as well, and we will compare the conversions estimated based on both these methods. Thank you.